Hello, I'm Sefgi and welcome. Our universe is a restless ocean with space and time themselves rippling and waving. LIGO detects the sharp splashes from colliding black holes, but what about the slow, deep swells? Gravitational waves with wavelengths measured in light years? Detecting these requires an observatory the size of our galaxy. Enter NANOGrav, the North American Nanohertz Observatory for Gravitational Waves. By monitoring millisecond pulsars, dead stars spinning with atomic clock precision, NANOGrav can sense the subtle stretching and squeezing of space-time from these immense waves. Today we'll explore how NANOGrav turns dead stars into a galaxy-sized detector, and what this new cosmic music reveals about our universe. To truly appreciate the groundbreaking work of NANOGrav, we first need to understand the nature of gravitational waves. These enigmatic phenomena are at the heart of their research, and unlocking their secrets could revolutionize our understanding of the cosmos. Einstein's theory of general relativity revealed that space and time are not separate entities but rather form a single dynamic fabric known as spacetime, a four-dimensional continuum that governs the behavior of gravity. This fabric isn't static, it's constantly being disturbed and reshaped by massive objects as they move through the universe. Planets orbiting stars, stars orbiting galactic centers, all contribute to this cosmic dance. When incredibly dense objects like black holes or neutron stars spiral together in a binary system, their interaction creates particularly strong disturbances. As these massive objects whirl around each other, they send out ripples through spacetime. These are gravitational waves, propagating outwards like waves on a pond. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is designed to detect high-frequency gravitational waves, those sharp, fleeting chirps that signal cataclysmic events like stellar collisions and black hole mergers. These are powerful but short-lived events. But beyond these dramatic bursts, there's a deeper, more subtle rhythm to the universe, a background hum of nanohertz gravitational waves with incredibly long cycles lasting not seconds or minutes but years, even decades. These waves possess wavelengths that are truly staggering, spanning distances of light years. To put that in perspective, that's many times the size of our solar system. LIGO, with its design optimized for high-frequency events, is fundamentally blind to these slow, vast waves. It simply isn't equipped to detect them. These ultra-low-frequency waves are primarily produced by supermassive black holes that dwarf our sun, possessing masses millions or even billions of times greater. These behemoths slowly orbit each other in the aftermath of galaxy mergers, locked in a gravitational dance that unfolds over eons. To detect these waves, we need a detector of truly cosmic proportions, something as big as the galaxy itself, and that's precisely where pulsar timing arrays like NANOGrav come into play. They patiently listen for this deep, persistent hum, a background gravitational wave signal created by the combined effect of countless supermassive black hole pairs scattered throughout the universe. It's like trying to discern a single voice in the roar of a stadium crowd, not just a single shout. The signal is a composite of many sources. LIGO, in essence, hears the universe's screams, the loud, sudden noises of cosmic collisions. NANOGrav, on the other hand, listens for its heartbeat, the subtle underlying rhythm of the cosmos. To achieve this remarkable feat, we use the stars themselves as cosmic buoys, delicately floating on the subtle tides of spacetime. So let's delve deeper and meet these remarkable stars that make this all possible. How do you build a galaxy-sized observatory? You use what the universe already provides. NANOGrav isn't a single telescope, but a collaboration using giant radio dishes like Green Bank and formerly Arecibo. These telescopes monitor an array of pulsars, nature's most reliable clocks, scattered across the Milky Way. This network forms a pulsar timing array, treating the space between Earth and each pulsar as the arms of a vast gravitational wave detector. NANOGrav is part of a global effort, the International Pulsar Timing Array, joining forces with European and Australian teams. By combining data, they boost sensitivity and confirm that signals are real, not local noise. The work is painstaking. Years of weekly observations building a massive dataset of pulse timings. Sophisticated algorithms sift through torrents of data, isolating the faint signature of gravitational waves. NANOGrav is a new kind of observatory, distributed, persistent, and built from the fabric of spacetime itself. It's a testament to scientific vision and collaboration. To detect these subtle ripples in spacetime, NANOGrav relies on some of the universe's most peculiar and strangest objects, pulsars. These celestial bodies act as incredibly precise timekeepers, allowing scientists to measure the minute distortions caused by gravitational waves. Pulsars are neutron stars, the ultra-dense remnants of massive stars. These remnants are the dense, collapsed cores left after supernova, the explosive deaths of massive stars. These stellar corpses are not quiet, they are spinning rapidly, often at incredible speeds, and possess intense magnetic fields. As they spin, their magnetic poles emit beams of radio waves like powerful spotlights cutting through the darkness of space. These beams sweep across space like lighthouse beams, creating a rhythmic pulse as they cross our line of sight. If Earth happens to be in the path of one of these beams, we detect a pulse with each rotation of the neutron star. This creates a cosmic clock of extraordinary precision, rivaling even the best timekeeping devices we have here on Earth. Among these pulsars, NANOGrav specifically uses millisecond pulsars, a special class of these objects. Millisecond pulsars are unique because they spin hundreds of times per second, making them exceptionally stable and reliable. Their rapid and consistent spin is often stabilized by accreting matter from companion stars in binary systems. These millisecond pulsars are the most reliable clocks in the cosmos, offering unparalleled accuracy for astronomical measurements. Their stability rivals that of the best atomic clocks on Earth, making them ideal for detecting subtle changes in spacetime. For each pulsar in its array, NANOGrav precisely predicts the arrival times of pulses, down to within mere nanoseconds. If spacetime were perfectly undisturbed, these pulses would arrive exactly on schedule, ticking away with perfect regularity. However, a passing gravitational wave stretches or squeezes space itself, causing the pulses to arrive slightly early or slightly late. The effect of these waves is incredibly tiny, causing variations in arrival times of only tens to hundreds of nanoseconds. Despite its minuscule scale, this effect is detectable with sophisticated instruments and careful analysis. By meticulously monitoring dozens of pulsars scattered across the sky, NANOGrav aims to identify a correlated pattern of these delays and advances in pulse arrival times. This specific pattern, a unique signature, is described by the Hellings and Downs curve, a theoretical prediction for how gravitational waves should affect pulsar timing. Finding this distinctive pattern in the data would be the smoking gun, providing definitive evidence for the existence of gravitational waves. In this way, these dead stars, the remnants of supernovae, become a living spacetime observatory, allowing us to explore the universe in a completely new way. After 15 years of patient observation, NANOGrav found compelling evidence for a stochastic gravitational wave background. This isn't a single note, but a persistent random hum, overlapping waves from all directions. The timing variations across pulsars match the unique Hellings and Downs signature predicted for gravitational waves. Our galaxy is bathed in a sea of low-frequency gravitational waves, the collective voice of supermassive black hole binaries. Imagine buoys on a choppy lake, no single wave but a correlated bobbing from countless overlapping ripples. NANOGrav measured these correlations, matching Einstein's predictions. The signal is faint, space-time stretched by just one part in a quadrillion, yet detectable across light years. This discovery gives us a new sense. We're not just seeing the universe, but hearing its deep, continuous hum. For the first time, we're cosmic acousticians, listening to the music of space-time. The era of gravitational wave astronomy is just beginning. The universe's deepest rhythms are now within our reach, and the music is only getting louder. What's making this cosmic hum? The leading suspect: binary supermassive black holes at the centers of merging galaxies. As these giants orbit, they radiate low-frequency gravitational waves, NANOGrav's specialty. The background is likely the sum of signals from millions of such pairs across the universe. But other, more exotic sources are possible, like cosmic strings, hypothetical defects in spacetime from the universe's earliest moments. If detected, cosmic strings would revolutionize physics, offering a glimpse into the universe's first second. There's also the possibility of primordial gravitational waves from cosmic inflation, the Big Bang's explosive birth. While the current signal is likely too strong for inflation alone, future measurements could reveal these ancient ripples. For now, supermassive black hole binaries are the prime suspects, but the search for new physics is just beginning. NANOGrav has opened the door to a universe of questions. Detecting nanosecond shifts in signals that have traveled thousands of years is a monumental challenge. Radio telescopes must be exquisitely sensitive, and timing equipment must log pulses with atomic precision. The data is messy. affected by interstellar plasma, Earth's motion, solar wind, and even pulsar glitches. Astronomers correct for these effects using multi-frequency observations and precise models of the solar system. Each pulsar's quirks, spin-down glitches, must be accounted for. All these noise sources are far larger than the gravitational wave signal itself. The key is the unique correlated pattern of timing variations across the sky, a fingerprint only gravitational waves can produce. Years of data and supercomputer analysis are needed to tease out the faint cosmic hum from the noise. It's a triumph of patience and precision and data science. This is the meticulous work behind every great discovery. Why does this discovery matter so profoundly? What implications does it hold for our understanding of the universe and our place within it? NANOGrav, through years of dedicated research and innovative techniques, has essentially built a new kind of observatory, a novel instrument for observing the cosmos. It's a galaxy-sized instrument, spanning vast cosmic distances, probing the universe in ways that were simply never before possible, opening up entirely new avenues of investigation. We now have direct, compelling evidence, gathered through meticulous observation and analysis. This evidence confirms that supermassive black hole binaries not only exist, but are relatively common throughout the universe, residing at the hearts of many galaxies. This discovery is fundamentally reshaping our understanding of galaxy evolution, forcing us to reconsider the processes that govern how galaxies form and change over cosmic time. The gravitational wave background provides a unique tool that lets us study in detail how galaxies merge and interact with one another. We can now observe how their central black holes interact during these mergers, gaining insights into their dynamics and eventual coalescence. It's also a completely new and independent test of Einstein's theory of general relativity, but now conducted on the largest cosmological scales imaginable. The observed signal aligns remarkably well with theoretical predictions, bolstering our confidence in the current models. However, future deviations from these predictions could potentially reveal entirely new physics, hinting at phenomena beyond our current understanding. Pulsar timing arrays hold the potential to one day detect signals from exotic objects like cosmic strings or even primordial gravitational waves generated in the very early universe. This would offer an unprecedented window into the universe's first moments, providing invaluable information about the conditions that prevailed shortly after the Big Bang. And as the sensitivity of these pulsar timing arrays continues to improve, we might even be able to pick out the signals from individual supermassive black hole binaries, identifying them as distinct sources. We could then watch their slow-motion dance across the cosmos in real time, observing their orbital evolution as they spiral closer together. This groundbreaking discovery is truly just the beginning of a new era in astronomy. It's akin to Galileo's first use of the telescope, opening up an entirely new way of observing and understanding the universe around us. We're essentially adding sound to what was previously a silent movie of the cosmos, giving us a richer and more complete picture. This allows us to reveal its full dynamic nature, capturing the intricate movements and interactions that shape the universe. NANOGrav has effectively opened the door to exploring some of the universe's deepest and most profound mysteries. The story of cosmic structure and evolution is now a symphony of gravitational waves, a symphony that we can finally hear and interpret. And what we've detected so far is only at the overture, with so much more to be discovered and understood in the years to come. For centuries, the cosmos was silent, a ballet of light and shadow. Now we can listen. LIGO hears the sharp chirps of colliding black holes. NANOGrav captures the deep hum of supermassive black holes. We are the first generation to hear this cosmic symphony. This is an invitation to curiosity, to ask new questions about the universe's secrets. The universe is speaking in a new language and we're just learning to listen. Keep looking up. And now, keep listening.